Hello everyone, welcome back to Empower Aspire. In this video, we will discuss the construction of a synchronous motor, including the stator, rotor, slip rings, brushes, and damper winding. We will also learn how the motor works on the principle of magnetic locking between the stator's rotating magnetic field and the rotor's magnetic field. In addition, we will cover synchronous speed, starting methods, types of synchronous motors, and their industrial applications. By the end of this video, you will have a clear understanding of why a synchronous motor runs at constant speed and how it differs from an induction motor. So, watch the video till the end and strengthen your electrical engineering fundamentals. If you find this video helpful, please like, share, and subscribe to Empower Aspire for more electrical engineering concepts, CBSE content, English vocabulary, and competitive exam preparation. Let's get started. A synchronous motor is an AC motor that operates at a constant speed known as the synchronous speed. Unlike induction motors, the rotor of a synchronous motor rotates at exactly the same speed as the rotating magnetic field produced by the stator. Because of this unique characteristic, synchronous motors are widely used in applications where constant speed operation is required regardless of load variations. Synchronous motors are commonly used in power plants, industries, compressors, pumps, conveyors, paper mills, and other large industrial applications. They are also used for power factor correction in electrical systems. Definition: a synchronous motor is an AC motor in which the rotor rotates at the same speed as the rotating magnetic field produced by the stator and maintains synchronization with the supply frequency. Construction of a synchronous motor. The main parts of a synchronous motor are 1. Stator. The stator is the stationary part of the motor. Features: made of laminated silicon steel. Contains 3-phase armature windings. Connected to a 3-phase AC supply. Function: produces a rotating magnetic field when energized. 2. Rotor. The rotor is the rotating part of the motor. Features: carries field windings. Supplied with DC excitation through slip rings and brushes. Function: produces a constant magnetic field. Rotates in synchronization with the stator field. 3. Slip rings and brushes. These components supply DC current to the rotor winding. Function: transfer DC power from an external source to the rotating rotor. 4. Shaft. The shaft is mechanically connected to the rotor. Function: transmits mechanical power to the load. 5. Damper winding. Damper windings are embedded in the rotor poles. Functions: help in starting the motor. Reduce oscillations during operation. Principle of operation. A synchronous motor works on the principle of magnetic locking between the rotating magnetic field of the stator and the magnetic field produced by the rotor. When a 3-phase AC supply is given to the stator winding, a rotating magnetic field is produced. The rotor is excited with DC current, creating a stationary magnetic field around it. The rotor poles are attracted by the rotating magnetic field of the stator. Once synchronization is achieved, the rotor rotates at exactly the same speed as the rotating magnetic field. Thus, the rotor and stator magnetic fields lock together magnetically and rotate at the same speed. Working of a synchronous motor. Step 1. Supply to the stator. A 3-phase AC supply is applied to the stator winding. Step 2. Formation of rotating magnetic field. The stator produces a rotating magnetic field at synchronous speed. Step 3. DC excitation to rotor. A DC supply is given to the rotor winding through slip rings and brushes. Step 4. Magnetic attraction. The rotor magnetic field interacts with the stator magnetic field. Step 5. Synchronization. The rotor accelerates and locks with the rotating magnetic field. Step 6. Constant speed operation. The motor continues to rotate at synchronous speed regardless of load changes. Synchronous speed. The synchronous speed depends on the supply frequency and the number of poles. N S equals P 120 F, where Ns equals synchronous speed, RPM, F equals supply frequency, HC, P equals number of poles. Example: if frequency equals 50 Hz, number of poles equals 4, then Ns equals 120 times 50, 4. Ns equals 1500 RPM. Thus, the motor runs at 1500 RPM. Why a synchronous motor is not self-starting? One major drawback of a synchronous motor is that it is not self-starting. When AC supply is first applied, the stator magnetic field rotates at synchronous speed. The rotor cannot instantly reach that speed. Therefore, synchronization does not occur immediately. To overcome this problem, damper windings are provided. Separate starting methods are used. Starting methods of synchronous motor. 1. Damper winding method. The damper winding acts like the rotor of an induction motor during starting. Advantages. Simple, reliable. 2. Pony motor method. A small auxiliary motor brings the rotor close to synchronous speed before synchronization. 3. Variable frequency drive, VFD. The supply frequency is gradually increased until synchronous speed is reached. Types of synchronous motors. 1. Non-excited synchronous motor. Examples. Reluctance motor, hysteresis motor. Applications. Clocks, timing devices. 2. DC excited synchronous motor. Uses DC excitation for rotor winding. Applications. Industrial drives, large power systems. 3. Permanent magnet synchronous motor, PMSM, uses permanent magnets on the rotor. Advantages. High efficiency, compact size. Applications. Electric vehicles, robotics, CNC machines. Advantages of synchronous motors. 1. Constant speed operation. The speed remains constant regardless of load. 2. High efficiency, suitable for large power applications. 3. Power factor improvement, can operate at leading power factor. 4. Better voltage regulation, helps maintain system voltage. 5. High power capability, suitable for heavy industrial loads. Disadvantages of synchronous motors. 1. Not self-starting, requires special starting methods. 2. Higher cost, more expensive than induction motors. 3. Complex construction, requires DC excitation system. 4. Maintenance requirements, slip rings and brushes need periodic maintenance. Applications of synchronous motors. Industrial applications, compressors, pumps, blowers, crushers, conveyors, power systems, power factor correction, reactive power compensation, manufacturing industries, paper mills, cement plants, textile industries, steel plants, modern applications, electric vehicles, robotics, CNC machinery, renewable energy systems. Synchronous condenser. A synchronous motor running without mechanical load is called a synchronous condenser. Purpose. Improve power factor, supply reactive power, enhance voltage stability. It is widely used in substations and power systems. Comparison between synchronous motor and induction motor. Synchronous motor. Induction motor runs at synchronous speed, runs below synchronous speed. Requires DC excitation, no DC excitation required. Not self-starting. Self-starting. Constant speed varies slightly with load. Can improve power factor, generally operates at lagging power factor. Higher cost, lower cost. Conclusion. A synchronous motor is an important AC motor that operates at a constant speed equal to the synchronous speed determined by supply frequency and number of poles. It consists of a stator carrying 3-phase windings and a rotor supplied with DC excitation. The motor works on the principle of magnetic locking between the stator's rotating magnetic field and the rotor's magnetic field. Synchronous motors offer high efficiency, constant speed operation, and power factor correction capabilities, making them ideal for industrial drives and power system application. If you find this video helpful, please like, subscribe. Empower Aspire. Thank you.